Okay, let's unpack this. If you're following the explosive growth of artificial intelligence, you know that when we talk about applying LLMs in the highest stakes domains, I'm thinking especially medicine, we run into this huge paradox.
Right.
These models are incredibly fluent. They can speak doctor perfectly, but they are just notoriously unreliable. They make things up, they hallucinate, and sometimes they do it brilliantly.
And that phenomenon, it creates the ultimate trust deficit. I
Yeah.
mean, if a system generates advice that sounds clinically perfect but is factually wrong, or you can't trace the evidence trail for it,
You can't use it.
you simply cannot adopt it in a setting where lives are on the line.
That's the core challenge we're digging into today.
Yeah.
You've provided sources covering 4, frankly, monumental breakthroughs. We're talking everything from drug analysis to fundamental changes in how AI even learns. And the mission for this deep dive is to connect these different efforts. We're going to show you how the field is systematically forcing AI to evolve from, a helpful but sometimes wildly unreliable generalist into a truly verifiable, reliable domain expert.
And that evolution, it requires a complete shift in perspective. The key obstacle for medical AI today is moving past simple statistical pattern recognition.
Which is what they're so good at.
It's what they excel at. But we need to get to grounded reasoning. And grounded means every piece of advice, every diagnosis has to be transparent, traceable, and based on verifiable step-by-step logic. The moment an LLM starts producing fluent but just plain wrong content, we have to build walls around it.
So let's start with one of those walls, a direct assault on the hallucination crisis in drug analysis, using a system known as DrugGPT. The immediate danger here is massive, right? If you use a generic open-ended LLM, it could recommend a wrong dosage, cite a study that doesn't exist.
Or give you flawed advice on drug interactions. Yeah, it's a complete non-starter in the clinic.
Absolutely. So how does DrugGPT solve this?
Its success really hinges on something called stringent knowledge grounding. It completely bypasses the model's internal, often hazy, pre-trained memory.
Okay, so it's not thinking for itself, so to speak.
Not in that way, no. Instead, it grounds its output strictly in clinical standard external knowledge bases, the gold standards. We're talking about trusted sources that clinicians already rely on, like drugs.com, the UK's National Health Service, and PubMed.
Now that sounds simple on the surface, just connected to a database. But the brilliance seems to be in the architecture. Why does DrugGPT need to be a collaborative mechanism? I mean, why use 3 specialized models? Why can't one big LLM just handle it?
That's a great question, and it speaks directly to accountability. Think of this system like a medical peer review board that's built right into the software. You wouldn't want one person doing every single job.
Okay, so walk us through how that board works.
So the first model is the inquiry analysis model. Its only job is to parse the user's complex question. It's like the intake specialist.
So if I ask about a disease, symptoms, a couple of drugs.
Exactly. It identifies all the required pieces and figures out exactly what knowledge is needed to answer that question.
It defines the search parameters.
Precisely. Then that request goes to the second model, the knowledge acquisition model. This is your expert retriever. It's engineered to efficiently extract only the relevant evidence-based snippets from those huge trusted knowledge bases.
It's not just a keyword search.
No, it's pulling out specific facts needed to answer the question.
And then the third model takes that verified evidence and builds the answer.
That's the evidence generation model. And crucially, it uses these really smart prompting strategies to keep it from wandering off script. One is called knowledge consistency prompting, which forces the model to generate text only using the evidence it was given.
Nothing else.
Nothing else. And the other, evidence traceable prompting, makes sure the model displays the source knowledge right there alongside the answer. It gives the clinician immediate verification. That verifiable trail is just key to building trust.
And the results really speak for themselves. I mean, DrugGPT achieved performance competitive with human experts on medical board exams, like the Mid-QA USMLE. But for you, the person listening, the safety metrics are what really matter.
That's right. When you look at high-risk tasks like identifying adverse drug reactions, or ADE, and spotting dangerous drug interactions, DDI DrugGPT showed massive improvements.
Massive.
We're talking absolute increases in accuracy from 17.3% up to almost 40% compared to state-of-the-art models like GPT-4. That's not a small gain. That is the difference between a potentially harmful suggestion and a reliable clinical fact.
And what's really powerful to me is its ability to handle novelty. The sources pointed out that it generalized, it performed accurately on brand new data sets, something like COVID and Moderna. That means it can process and integrate knowledge about new drugs that the base models were never trained on.
It can grow its knowledge without being retrained from scratch. That's huge.
Okay, so DrugGPT basically solves the hallucination problem for text by chaining knowledge and forcing verification.
Right. But that brings us to the next much harder challenge. What happens when the AI doesn't just hallucinate a fact, but hallucinates where a tumor is, or misidentifies a lesion in 3D space?
We're moving from language reliability to spatial grounding.
Exactly. Which takes us into the world of 3D medical images like knee MRIs and the development of 3D reasoning. This introduces a whole new level of complexity.
Because diagnosis isn't just about spotting something. It's about a very precise sequence of steps.
Precisely. When a clinician assesses a complex 3D image, they use this structured region-first workflow. They have to first pinpoint a specific anatomical subregion, say a part of the femur, then assess the severity of the finding in that exact spot, and finally assign a structured grade, often using a framework like MOACUS.
And the standard vision language models, the VLMs, just fall apart here.
They do, because the existing 3D datasets, they're okay at basic localization, but they don't capture that crucial step-by-step diagnostic reasoning chain.
That was the gap.
That was the gap. And 3D reasoning addresses it by creating this new data set of extraordinary quality built from almost 8,000 3D knee MRI volumes. And the key component is what the researchers call quintuples.
Quintuple. Okay, let's clarify what that is, because it sounds a bit esoteric, but it's really the formula for an auditable diagnosis, isn't it?
That's a perfect way to put it. Think of it as 5 perfectly linked pieces of evidence for every single case. You have the MRI volume itself, the specific diagnostic question being asked,
Okay.
the 3D bounding box that pinpoints the exact physical location, the clinician-generated reasoning steps, the human chain of thought, and then finally the structured severity assessment, the grade.
That is just incredible dedication. The sources noted this required over 450 hours of expert clinician time just to manually segment MRIs and write out those explicit reasoning chains.
They literally built the audit trail for the AI to follow. And when they ran benchmarks on this gold standard data, they made an astounding discovery about AI's main weakness.
What stood out when they tested the models on it?
The key insight was that grounding is the major failure point.
Grounding is in finding the right spot.
Finding the right spot. So when they tested the models normally, the models struggled with the final diagnosis. But then they ran a control test. They gave the model the ground truth region. They just eliminated the localization step.
So they told the model, hey, the problem is right here.
Exactly. Here's exactly where the problem is. When they did that, the overall diagnostic accuracy improved by 0.05.
Now, 0.05 might sound small, but in these critical tasks, that represents a substantial number of corrected diagnoses.
It's a huge deal. What it proved was that the model often knew how to reason. It knew how to grade the severity according to the framework. The failure happened because it couldn't reliably and correctly localize the pathology in that complex 3D space. The model knew the answer, but it couldn't point to the right spot.
So if the problem is all about verifiable, auditable reasoning and factuality, many AI researchers are looking backward to symbolic systems for inspiration, which leads us to this neurosymbolic trade-off and systems like GraphMERT.
This is really the fundamental dilemma facing all advanced AI. On one side, you have symbolic systems. Think of them like a hand-drawn map.
Yeah.
They offer rigor, complete interpretability. Every rule is explicit, but they just don't scale well to the messy complexity of, say, millions of scientific papers.
And on the other side, the neural systems, the LLMs, they're the GPS.
Right. Fast, scalable, flexible, but ultimately they're black boxes. They're prone to being opaque and, as we've already established, to hallucination.
So where do knowledge graphs, or KGs, fit in?
KGs are the compromise. They are the critical link in neurosymbolic AI. A KG is a highly structured symbolic memory bank made of these explicit triples: a head, a relation, and a tail. It's an auditable rule repository.
And GraphMERT is designed to build these.
Exactly, to efficiently and reliably build these high-quality, domain-specific KGs directly from raw, unstructured text.
So why do we need a specialized system like GraphMERT? I mean, why can't I just ask GPT-4 to extract facts into triples? Why would it fail?
Because generic LLMs don't respect the underlying structure of knowledge, which is called an ontology. Ontology basically defines what can be linked to what. GraphMERT uses these sophisticated networks to encode both the text and the relationships, and that allows it to enforce these ontological constraints that generic LLMs just completely ignore.
Can you give us a really memorable example of an LLM failing this kind of test? Because it's hard to picture an AI making a structural error like that.
The sources documented this fantastic reverse test. Researchers prompted a state-of-the-art LLM to infer relations about chronic kidney disease, or CKD,
Okay.
and the model hallucinated an ontologically invalid triple. It misused the relation has finding site to link chronic kidney disease to cerebellar gray matter.
Wait, chronic kidney disease is about the kidneys, but the model linked it to the brain.
Exactly. Based on medical ontology, the correct finding site should always be the kidney structure. The model made a fundamental semantic error. It confused two things appearing in the same text with a valid relationship. We also see them creating totally invalid triples, like linking diabetes to mammography, just because the words appeared near each other.
So they get confused by context and link things that should never be linked. That is the very definition of unreliable knowledge.
Precisely. And that's why GraphMERT's KGs are significantly more reliable. They show higher factuality and validity scores because it enforces those constraints. It links concepts globally across the whole data set, not just locally based on one sentence. It creates knowledge that's cleaner and, ready for trustworthy deployment.
Okay, so we've talked about external grounding, DrugGPT, using databases, GraphMERT building KGs and grounding visual data with 3D reasoning. Now let's go even deeper into the internal architecture, because the final piece of this puzzle is about transforming the AI itself so it can truly become a dynamic expert. This brings us to a new paradigm, nested learning.
This architecture tackles one of the most compelling challenges in LLMs today. And we can sum it up with I think, a pretty compelling analogy. Current LLMs suffer from a form of anterograde amnesia.
Anterograde amnesia, the inability to form new memories after an event, like in the movie Memento.
Exactly like that. Their knowledge is split into two static buckets. You have the immediate context window, which is temporary short-term memory, and then you have the frozen long-past pre-training knowledge, which is deep in its layers. If you teach it a new fact today, once that context window scrolls past, it can't consolidate that into a new long-term memory. The model stays static.
So it's constantly reliant on old facts or these external retrieval systems. It can't truly evolve on its own.
And nested learning, or NLL, fundamentally reimagines deep learning to solve this. It views the whole training process as a set of nested, multi-level optimization problems. Each one operates at a different, explicitly defined update frequency. It's not just about adding more layers, it's about giving the model structural dynamic memory.
And the most mind-bending insight from this work is what it reveals about gradient descent, the basic math we use to train all these models.
Right. NL demonstrates that standard gradient-based optimizers, like Momentum, they aren't just mathematical tools. They are fundamentally acting as associative memory modules. They compress the local surprise signal, the new information learned in a moment, into their own parameters.
So the training process itself is a form of memory.
It's a form of memory, and this revelation allows researchers to design highly expressive optimizers with deep memory, moving beyond simple compression into true consolidation of knowledge.
Which leads us directly to the creation of HOPE.
HOPE stands for Hierarchical Reasoning Model. It's built on these nested learning principles, and it introduces what they call a continuum memory system that moves past that static memory problem. The key is that HOPE enables the model to learn its own update algorithm.
It learns how to learn.
It learns how to learn. It creates a truly self-modifying sequence model. So instead of just relying on its fixed pre-training, it can dynamically change its own parameters based on new, evolving clinical context. It can effectively form new, stable long-term memories from novel input. It escapes the pre-training cutoff date forever.
So if we pull these four breakthroughs together, DrugGPT, 3D reasoning, GraphMERT, and nested learning, what does this multi-front war on reliability really mean for the medical AI you'll interact with?
I think it means the industry has finally identified that trust requires dual accountability. Trustworthy AI has to have rigorous external grounding.
That's DrugGPT and GraphMERT.
Exactly. DrugGPT's reliance on databases, GraphMERT's construction of auditable knowledge graphs. That's one side of the coin.
And the other side is an equally profound change in internal structural reasoning.
Yes. That's the ability to correctly localize findings in 3D space, which 3D reasoning proved was the biggest bottleneck. And it's the dynamic memory and self-modification that's promised by nested learning and HOPE. The path forward is paved with explicit, auditable structures on the outside and dynamic learning on the inside.
You know, the 3D reasoning work, it established a framework for longitudinal reasoning, assessing disease progression in a knee over multiple time points. It moved the AI from just diagnosis to something closer to prognosis.
Right, they're training the model to look forward in time.
So here's the final thought. If models like OP can successfully overcome this AI anterograde amnesia, if they can continually consolidate new knowledge and new memories from every new clinical input, how quickly will medical AI transition from just providing static diagnoses based on old knowledge to accurately predicting long-term patient prognosis and dynamically adjusting treatment plans based on real-time, evolving clinical data?
That is the ultimate test, isn't it? Of reliability and true expertise. It suggests a future where the AI's knowledge base doesn't stop growing the moment it's deployed. Instead, it grows smarter every single time a clinician uses it.
Something to mull over as you keep digging deeper into these foundational shifts in AI architecture.